Hello everyone, welcome to today's live broadcast, Getting the Best Out of Solid Core Technology for Small and Large Molecule Analysis. I'm Alistair Matheson, the Editor-in-Chief of LCGC, and I will be your moderator for today's event. We're very pleased to bring you this webcast presented by LCGC and sponsored by MacMod. Here is a statement from our sponsor. A company should be able to condense its mission statement into a simple phrase. MacMod's mission statement is smarter chromatography, but you may ask, what does smarter chromatography actually mean? It means that when a customer makes when the company makes a recommendation to you about an HPLC or UHPLC product, it is to partner with you to offer innovative solutions to your complex problems. They use advanced state-of-the-art analytical software to match their product portfolio with your separation needs. MacMod leverages their 30-plus years of experience in the LC column business, their technical expertise and manufacturing network to help you solve your toughest application problems. They provide up-to-date and accurate technical catalogues and reports from industry-leading separation scientists to keep you informed of new technologies. We have a few important announcements before we begin. This webcast is designed to be interactive and we encourage you to ask questions during the event. You can submit questions by typing them in the Q&A box, which can be found on the right-hand side of your screen. You can enlarge the slide window by clicking on the small square icon in the upper right-hand corner of the slide window, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size. The slides will advance automatically during the event. If you have any technical problems viewing or hearing this presentation, please click on the question mark help widget in the dock at the bottom of your presentation window. I would now like to introduce today's speaker. We are very pleased to be joined today by Matt James, PhD. Matt James is a Senior Research Scientist at Avantor Sciences. Matt gained his PhD at the University of Bristol in the UK, working on the analysis of archaeological samples, and also worked within the pharmaceutical industry for a year. Over the last 11 years, he has worked with the technical support applications and R&D teams within Hycron, which is now part of Avantor. Recent focuses have been HPLC, UHPLC method transfer and translation of the use of solid core phases, development of next generation LC stationary phases, and the development of LC methods for key applications, such as the analysis of nitrosamines by LC-MS. Matt has co-authored 7 peer-reviewed articles and patented work at several presented work at several conferences. And thanks very much for joining us today, Matt. If you could start the presentation, that would be great.
Okay, thanks very much for the kind introduction, Ali. I'd like to start by just saying a warm welcome to everyone. Thank you very much for joining us for this webcast today. It's my pleasure to be talking today about solid core particles and their application in LC analysis for both small and large molecules. They're very interesting particles from a chromatographics perspective and can provide us with some very useful benefits over traditional fully porous particles. So hopefully today's talk will be informative and give you an idea about how to get the best out of these particles. So before I start, I just wanted to say a very quick thank you to our sponsor, MacMod, for inviting me to present today. MacMod have a wealth of expertise, as we said, in separation science, particularly HPLC and UHPLC, and have been a trusted, authorized channel partner to us who we work very closely with over the last 20-plus years. So before we begin, I just want to give a quick overview of what I'm going to talk about today. We thought it would be interesting to start with a bit of information about the history of solid core particles. It's quite an interesting history. We tend to consider solid core particles as being quite a recent development in liquid chromatography, but actually they have their origins back in the 1960s. So it's quite useful to get a little appreciation of that. I'm then going to move on to looking at some of the advantages that solid core particles can offer us. So to look at that, we're going to model some of the kinetic performance of these particles, particularly look at dispersion theory, and then move on to a little bit of kinetic theory as well. So from there, I'm then going to talk a little bit about separating small molecules with solid core particles, look at how we develop methods, how we can try and get the best out of this type of particle for those types of separations. We then move on to looking at large molecules, so particularly proteins, as the name implies, they're much larger than the typical small molecules, so that there are a number of challenges associated with analysing those types of molecules. And throughout the talk, I want to just sort of throw in some method development considerations, examples of work that we've done in our lab, which will hopefully give some useful insights on how to develop methods with solid core particles. So if we move on to the history of solid core particles, as I mentioned, we tend to think of them as being quite a recent development, but actually they have their origins back in the 1960s. Hogarth and Lipsky first introduced the concept of pellicular or coarse shell particles. Essentially, they were working with large macromolecules, and they proposed that if they used a solid glass bead that was coated with a thin porous layer of resin or silica, they could improve the kinetic performance of the analysis for large molecules. And around the same sort of time, in the late 60s, early 70s, a number of other groups were also looking at this type of particle architecture, notably Jack Kirkland at DuPont, where they launched the Zipax particle, and also Corossil and Peresorb made it onto the market from Waters and Merck, respectively. Now, these particles are roughly about 50 microns in particle size, and crucially, due to the very thin porous shell on these columns, they tended to somewhat lack in loadability. And so they saw some success, but really were overshadowed by developments that were going on with fully porous particles. So at that sort of time, we were moving towards higher purity materials. We were moving away from irregular shaped particles to spherical particles, which gave much higher performance. And we also saw the introduction of smaller particle sizes. So 10 micron became fairly standard for fully porous particles. So that really inhibited the growth of solid core phases at that time. Then through subsequent decades, the 80s and 90s, we saw a general trend of decreasing particle sizes, first with 5 micron, then 3 micron. And then in the early 2000s, we saw a bit of a revolution, really, with the introduction of sub-2 micron UHPLC phases, particles rather. So these particles, as I'm sure many are aware, that they can produce very high efficiencies, and we can also operate them at quite high flow rates as well. So we can perform very highly efficient, very fast analyses. The disadvantage for those particles, of course, is that they generate very high back pressure, and that necessitated a redesign of the LC system and the introduction of UHPLC systems. So essentially, very low dispersion systems that could operate at 1,000 bar plus. And adopting UHPLC technology was financially a bit restrictive for many companies, so this sort of prompted a bit of a parallel line of thought, which was really, can we improve on the types of particles we're using? How can we get more, generate more efficiency from spherical particles? So in 2006, that led to the introduction of what's really the current generation of solid core particles, and essentially what they did to overcome the loading capacity issues with early particles is utilize a much thicker solid core. So even though we have a solid core to the particle, they are in fact about 75% or so porous. So what is a solid core particle? Well, this diagram on the right-hand side shows that we have a central solid core, which is then encapsulated or surrounded by this porous outer layer. These days, particle sizes in the range of 2.4 to 2.7 and also 5 micron are fairly typical. So within the ACE ultra core range, our solid core range, we have 2.5 micron particles and also 5 micron particles. Recently, we've introduced an extension to that line, which is based on a 3.5 micron particle, and that sort of expands the possibilities for the use of this type of material on standard 400 bar instruments. It's worth noting smaller particles are also available in the 1.3 to 1.7 micron range, but these are, due to back pressure restrictions, are primarily limited to UHPLC, use on UHPLC systems. So one parameter that you'll often see quoted, or one characteristic of solid core particles, is the rho value, and essentially that's the ratio of the solid core diameter to the overall particle diameter, and typically for solid core particles this falls in the range of around about 0.6 to 0.7. So how do we actually make solid core particles? Typically we use a layer by layer approach. You start off with that solid silica particle, you treat it with cationic polymer, and then addition of anionic silica nanoparticles means that you start to build up a layer of these silica nanoparticles on the surface of that central core. We then remove the polymer, wash it off, and then repeat this process over and over a period of several days, and we can build up that porous outer layer. And that's what you see on the SEM image on the right-hand side. You have the non-porous core in dark grey at the top right, and surrounding that is this porous layer of silicon nanoparticles with the interstitial spaces in white that give the porosity to that layer. There are other approaches available, for example, approaches that have been developed by Peter Myers at the University of Liverpool in the UK that can produce these core shell type particles in a one-pot synthesis. But to date, as far as I'm aware, this approach isn't really used commercially. So now we're going to move on to try and get an understanding of exactly why solid particles are so good. And to do this, we need to start by looking at dispersion theory, which was developed initially by Van Dienter and lastly by John Knox, who's shown in the photo here. So ideally, as a chromatographer, we want nice razor-sharp peaks, but in practical reality, this isn't possible. What happens is our analyte passes through the column, it diffuses, it spreads out. So we have a peak width associated with that peak. So diffusion theory helps explain this. We've got the diffusion theory on the screen here. Essentially, we consider the height equivalent theoretical plate as a function of the linear velocity or the flow rate of mobile phase through the column. HETP is essentially a measure of how broad the peak is, and it's inversely proportional to the efficiency. So the lower that oval curve in green that we obtain sits within that plot for a given particle, the higher efficiency we can expect from that particle. So broadly speaking, the dispersion process on a column is broadly the sum of three different terms: the A term, the B term, and the C term, as we've got shown on the screen. The A term relates to eddy diffusion, or the different pathways a molecule can take when passing through the column. And the A term is essentially improved through the use of smaller particles and also through better packed columns as well. The B term relates to the longitudinal diffusion. As an analyte moves down the column, it tends to diffuse with time and essentially spread out and broaden. You can see from the light blue curve on the screen there, which represents the B term, that it's highly dependent on the linear velocity and is particularly impactful at low flow rates. And then finally, we have the C term, which relates to mass transfer in and out of the stationary phase. And the way I tend to think of this is that if we have two analyte molecules entering the column at the same time, particle A or molecule A diffuses into and then out of the stationary phase, and in the time that's taken to do this, particle B will have moved further down the column. So essentially, the two molecules have dispersed from one another. They've moved apart. Our peaks dispersed. So we now consider some experimental plots that we've generated for both fully porous and solid core particles. We can start to understand some of the benefits that solid core particles can offer us. So if we firstly consider a 3 and a 5 micron fully porous particle, so those are the traces shown in blue on the left-hand side, you can immediately see that the 3 micron curve sits much lower, and so as expected delivers high efficiency compared to that 5 micron fully porous particle. You'll also note that the optimum linear velocity, so that's the minimum on these curves, actually lies at slightly higher flow rate with the smaller 3 micron particle. But if we now take a look at the 5 micron solid core particle, so the Avantorase ultra core particle, which is plotted in green, you can clearly see that despite having the same nominal particle size as the 5 micron fully porous particle, we're actually achieving much higher performance. We're achieving performance that's very similar to that 3 micron fully porous particle. And so there's an additional benefit or additional aspect to the attractiveness of the use of solid core particles. So on the right-hand side, we have back pressure, column back pressure, plotted as a function of flow rate. And as you can see, we're with that 5-micron solid core particle, we're achieving 3-micron-like performance, but at much lower back pressure. So these particles are ideal for really improving the efficiency generated on standard, i.e. 400 bar limited LC systems. So similarly, if we now consider a 1.7 micron fully porous UHPLC particle, which is plotted in the blue circles on the left-hand side there, we can again see that the curve, the Knox curve, sits much lower on the plot, so it delivers much higher efficiency. You'll also notice it's a much flatter curve as well, so we can run at higher flow rates without sacrificing any of that efficiency. So essentially with that type of particle, we can now run highly efficient separations and also run at high flow rates to generate very fast separations. But now look at the 2.5 micron solid core particle in green. The performance is strikingly similar to the UHPLC fully porous particle. Looking again at the back pressure, we're essentially getting that UHPLC performance at more or less 3 micron back pressure. So again, that 2.5 micron solid core particle can potentially be used on a standard LC system. So essentially, these plots are showing us that solid core particles produce a significant improvement in efficiency relative to their fully porous counterparts without the necessity to be working at UHPLC pressures. So clearly, the Knox plots, they demonstrate the advantage of solid core particles. That advantage is driven by improvements of all three of the dispersion terms that we discussed earlier. It used to be thought that it was primarily improvements in the C term that drove this performance improvement, but it's since been shown that it's primarily due to improvements of the A term. The A term is much reduced in solid core particles, and this is in part related to them packing quite nicely, so we get a very nice ordered packed bed. Essentially, what you find is these solid core particles have a degree of roughness to the surface, and from a column packing perspective, that actually helps us quite significantly. Similarly, the B term is improved significantly as well, longitudinal diffusion. So that's essentially dependent on the volume of liquid within a column. The volume of liquid within which our analyte peak can start to disperse. So naturally, if we take our particle, we replace a large amount of it with a solid core, we're reducing the internal volume of that column. So we're reducing the amount of liquid in that column, and our peak can therefore has less opportunity to disperse through time. But this doesn't tell us the full story. These plots give no indication of the analysis time that's required to generate the efficiencies we see, and it also gives us no guidance on any pressure limits as well. So to sort of further understand solid core particles, what I want to do is to take a little bit of a dip into some kinetic theory and consider some different ways to interpret the data that we've just seen. So firstly, we're going to plot the retention time versus efficiency. So as chromatography, the ideal situation is that we want to produce very high efficiency separations, and we want to do that in as short a time as possible. So in terms of this graph, what we want is a column that sits in the bottom right-hand corner. It delivers very high efficiency with very short run times. Now, plotted on here, we have a 2 micron fully porous particle in blue. We have a 3 micron fully porous particle in grey, and you can clearly see that the 2 micron offers that higher efficiency compared to the 3 micron. We also have the Avantor Ace UltraCore 2.5 micron solid core particle plotted in orange, and you can very clearly see that the solid core that provides the optimum performance here. And essentially what we're seeing is that it can produce much sharper peaks, much higher efficiency separations in less time. So for example, if we can view this by looking at if we wanted to get an analysis time of about 100 seconds, a 3 micron fully porous particle would generate around about 7,500 plates. A 2 micron would push up to maybe 8,500 plates, but with that solid core, we can start approaching efficiencies of close to 10,000 plates. So to take this a bit further, we need to consider pressure. And to do this, we introduce a new kinetic parameter, which is called impedance. And this was devised by John Knox and Paul Bristow at ICI in 1977. And essentially, impedance defines the resistance a compound has to moving down a column relative to the performance that column is providing. In essence, it's a measure of how much effort it actually takes to generate the efficiency on that particular particle. So E is defined according to the equation shown on the screen there. So we have the column, the pressure drop across the column, the retention time, and we also have an efficiency and mobile phase viscosity contribution to the term. So we can plot the impedance on a reverse axis, which essentially mimics a Van Diep's type plot. So on these plots, we're looking for the minimum value. So the lower a curve lies, the more optimum the conditions. So if we look at plotting the same data that we had a moment ago, we have now impedance on the right, or the amount of effort required to generate efficiency on the right, and efficiency plotted along the bottom. So again, we can see two things. It's immediately obvious that the ultra core, the solid core particle sits much lower here. So it's saying that we need to put in far less effort to generate our sub 2 micron performance that we saw earlier compared to a fully porous particle. You'll also notice that the two fully porous particles essentially sit one on top of the other. This might seem a little counterintuitive, but actually this is fully expected. In fact, we don't have the 1.7 micron data here, but that sits bang on top of those other two particles as well. And essentially what that's saying is, if we consider that we can, for example, generate 10,000 plates on a 2 micron column, well, you can also generate 10,000 plates on a 3 micron column. You just need to use a slightly longer column. And so consequently, the two, if the particles have the same morphologies, you get similar performance characteristics. The fact that they sit one on top of each other is actually a testament to the quality of the packing that we get out of the Hycron facility back in the UK. Essentially, it's showing those columns are both very well packed. So if we now move on to consider the separation of small molecules and see how we go about developing methods on these particles. So we're looking at reverse phase methods in particular here. So essentially the same principles apply to the development methods that would apply on fully porous particles. And we need to consider, as we mentioned, the back pressure. We consider the column dimensions, the particle size. Pore size is very important. For small molecules, we typically utilize pore size around about 90 to 100 angstroms. Pore sizes are a lot more critical for large molecule analysis, and we'll look at that a little bit later. Column chemistry is absolutely very important to consider, and again, we're going to look at that a bit more closely in a minute. And also things like the solvents we use, the temperature we're working at, and the pH. So when we're developing new methods, it sort of pays to take a step back and consider what we're actually trying to do, i.e. we're trying to achieve maximum resolution between our critical and light pairs. So here on the screen we have the Pinel equation, which essentially defines resolution as being a product of three individual terms. We have an efficiency term in blue, we have a selectivity term in red, which relates to our peak spacing, and we also have a retention factor term in green. Now, from the plot on the right-hand side, if we consider that, what we've done here is we've taken each of those individual terms, we've fixed the remaining two, and we've varied that term to see what impact it has on resolution. And hopefully you can see that it's quite apparent that the selectivity term has the biggest impact on resolution. So this is suggesting to us that in method development, it's absolutely selectivity of our separation that we need to focus our attention onto. It's not always the case. That there are, of course, occasions where investments in improving efficiency and improving the retention of your compounds is equally or more important. But in general, with method development, for a generalized method development activity, selectivity is absolutely the key to improving resolution and boosting performance. So what factors affect selectivity? So if we consider isocratic separations, we have column stationary phase, which is absolutely the most influential parameter that we can assess. And generally with method development, we would suggest screening your sample on multiple different stationary phases to try and optimize the actual selectivity obtained. If you're working with ionizable analytes, acids and bases, pH is also very critical, and you can move peaks around quite significantly by varying the pH of your mobile phase, and hence the ionization state of those analytes. Organic modifier type can be very powerful, so looking at whether you use methanol or acetonitrile, or perhaps even a blend of the two. Percent organic modifier is obviously important, and then to a lesser extent we have buffer selection, buffer concentration, and column temperature, which can really be used to sort of fine-tune a separation. With gradient separations, those same parameters are also important to consider, but this time we also have factors such as the gradient steepness, the gradient range, and also factors such as dwell volume can play a role. So what I want to do is look at this idea of column stationary phase selectivity and see how we can optimize that. So we consider this in selectivity in a very simple way by considering this simple separation on the screen. If we start with a C8 phase in the center, we can move to a more hydrophobic phase, a C18 phase, and we would expect to see stronger retention, which is exactly what we see. We see more hydrophobicity. Conversely, if we move to a less hydrophobic phase, a C4 phase, we get a decrease in retention, which we again see. But what you'll notice is that the selectivity of those separations, the spacing of those peaks is essentially pretty much unchanged here. We're just varying the relative retention time. And this is as expected because on all of these columns, the separation is primarily driven by hydrophobic interaction with the stationary phase. So what we need to do is consider using stationary phases that offer different analyte interactions. So if we move on and we consider moving this separation to, for example, a cyano phase at the top right, you can immediately see that we get a very different elution order. We get so in some cases, complete reversals of elution order, which is brilliant for method development. Equally, if we move the separation onto a phenol phase, it offers strong aromatic selectivity. Again, we see a very different separation. So we can really see how the power, the stationary phase chemistry, the selectivity that we can get from it can be very powerful in method development. And it gives us a very powerful platform to work on. And this is exactly what we try to introduce to a new range of columns in the Avantor ACE UltraCore range. On this new 3.5 micron particle, we have a C18 amide phase, we have a C18 phase, we also have a phenol hexyl phase and a biphenol phase. And these are designed to offer some very different selectivity for small molecules. And we can consider this, or we can show this by considering some characterization protocols, in this case the Tanaka characterization protocol, which is fairly well studied and routinely performed. And essentially what we've done here is plot the values, the Tanaka values that we obtained for those 4 stationary phases on a radar plot. So very briefly, K-amyl benzene refers to the retention factor of amyl benzene. That's a measure of hydrophobicity. The alpha AB value gives us an indication of hydrophobic selectivity. The alpha TO value gives us an idea of shape selectivity. Essentially, some stationary phases have a much more sort of rigid structure, and so can discriminate against analytes with different molecular shapes. The alpha CP value gives us an idea of the hydrogen bonding capacity a particular stationary phase has. And we also have various other terms that look at potential ionic interactions that are available at different pHs. And essentially what we can see from that plot is we can quite clearly distinguish between those different stationary phase selectivities. If we were to plot the C8, the C4, and the C18 that we saw on the previous slide, they'd essentially largely overlay apart from that retention of factor for AMR benzene. So what this means practically is that if we screen a sample on these different stationary phases, we can get very different separations, which is shown on the chromatograms in the right-hand side. So this is we have nice selectivity differences here that are really powerful for method development. So we mentioned that solid core columns can achieve high efficiency, very fast separations on HPLC systems. So I just want to take a minute to look at an example of exactly this. So at the top here we have a separation of aspirin and related substances, which is run on a fully porous super C18 phase. This produces a good separation and good resolution. And now at the bottom we have the same separation, which is run on the same conditions, same column dimensions, on a solid core particle, again 5 micron, with the same stationary phase chemistry, that super C18 chemistry. So firstly, you can see that we achieve our separation a lot quicker on the ultra-core column, and that's essentially because we have a reduced hydrophobicity for the solid core particle. Essentially, we've replaced a large part of that porous structure with a solid core, so it has much less surface area and hence overall reduction in hydrophobicity. Secondly, if we take a look at the efficiency, we're massively increasing the efficiency of the separation with that solid core particle. We were generating about 12,500 plates on the top separation, and on the solid core particle we're almost doubling that to 21,000. But again, as we mentioned earlier, we're doing that at what is essentially the same back pressure. There's very little difference in back pressure. You'll also note that we lose a little bit of resolution on the first 2 peaks there, and that's essentially due to this reduction in hydrophobicity. If we wanted to restore that, we could look at reducing the amount of organics slightly in our mobile phase to bring that back out. So I want to, at this stage, take a closer look at the first 2 peaks that you can see. You'll notice that these peaks are very narrow and show improved sensitivity or better peak height than on the fully porous columns. So these peaks can be used to highlight quite an important consideration if you're looking to use solid core particles to generate very highly efficient and narrow peaks. And that is, we need to pay very close attention to the detector settings that we use. So the top separation we ran with a detector rate of 2.5 Hertz, which was perfectly adequate to accurately record those early eluting peaks. So when we moved this separation to the solid core particle, however, if we keep that detector rate at 2.5 Hertz, we actually find we lose a lot of the resolution, and we had to, and we found that when we turn that detector rate up to the maximum on that system, so to 20 Hertz, then the situation was vastly improved. So this example really sort of illustrates that what we can achieve with solid core particles, and that is that we can, as we said earlier, we can use highly efficient separations and we can achieve them a lot faster. Before we move on, I just want to dip back into that idea of detector rate. I've got another example here. This time this is a UHPLC separation on a 2.5 micron ultra-core particle. So this example shows us that we can absolutely generate the high efficiencies promised with these particles and achieve very fast separations. Here we look at a range of detector settings, range from 2.5 Hertz at the top to down to 80 Hertz at the bottom, and we can see that essentially we do very much require faster detector rates to accurately record these narrow high efficiency peaks when we're generating these fast separations. The plot on the right shows that the detector setting is far more important for poorly retained analytes or those with a low retention factor. For better retained analytes, we can afford to work at perhaps 20 Hertz or so, but for those early eluters, we absolutely need to be working up at 40 to 80 Hertz. So another important factor to consider is extra column volume. We don't have time to discuss that today, but if anyone's interested in learning a bit more of that, I would strongly suggest either contacting MacMod or referring to their website. There's plenty of information available on that topic. So I just want to briefly run through a couple of applications that we've developed on these solid core particles. This is the separation of nitrosamine contaminants and a valsartan drug substance. This is very topical at the moment in the pharmaceutical industry. Essentially, we have to quantify these impurities at incredibly low detection limits. And so you require a very high efficiency column that's going to give you excellent sensitivity. And the solid core particles, the ACE Ultra Core, is ideally suited to that. And you can see here we can generate a very nice, highly efficient separation. We've since taken this further, and we've reduced the column ID, we've increased the flow rate, and developed that now into an LCM SMS application, a very high throughput application. So you can see even on a 3.5 micron particle size, we can generate some very nice separations. This next example shows a somewhat challenging example of separation of a set of phenolic compounds. We've achieved this separation on a C18 amide phase, an ultra-core C18 amide. Essentially, we find that amide phases have quite a good degree of phenolic selectivity, so in this case, it proved to be absolutely the best column for the separation. And then finally, I've got an example here of water-soluble vitamins, this time on a phenyl hexyl phase. Again, we generate a high efficiency, good peak shape, and in this case, we could quite easily consider moving that to a smaller column, perhaps increasing the flow rate to get a higher throughput method. So just to finish our discussion on small molecules, I just wanted to run through a quick example from our lab in how some seemingly trivial changes to a method can actually have quite unexpected consequences. So two colleagues of mine, Tony and David, were generating data for the NOx plots that we saw earlier. And essentially for this, you have ketoprofen on an isocratic separation, and as we vary the flow rate, we look at the efficiency obtained. Standard method for this protocol uses 0.1% TFA in the mobile phase, and you find that as you increase flow rate, the retention factor of ketoprofen remains constant, it's rock solid. So what they proposed was changing the TFA for formic acid, which seemingly made sense. It would make the method compatible with LCMS and seemed entirely reasonable on the face of it. However, what they found was that as the flow rate was increased, we actually saw a decrease in the retention factor of ketoprofen, which is rather unexpected. So what they then did was plot 1 over the retention time versus flow rate, which you see in the top right-hand corner, which gave a nice linear relationship. So everything looked okay from that perspective. But what they then did was use this calibration curve, if you like, to generate some predicted retention times, and looked at the accuracy of the experimental versus the predicted times. And this highlighted that there was a bit of an issue with the ketoprofen. It wasn't behaving as we expected. So if we consider ketoprofen, it's an acid with a pKa of around about 3.9. Above this value, or pH is above this value, we're looking at an ionized molecule, and below it we're looking at it in its neutral form. So the pH of 0.1% TFA, that original method, is around about 1.9. So we're well away from that pKa as we'd like to be. However, 0.1 formic acid has a pH of around 2.8 or so, and therefore we're starting to see a little bit of ionization of the ketoprofen. And of course, this ionization is an equilibrium process, and what we actually see is as we're increasing the flow rate, we're of course increasing pressure, and that increase in pressure absolutely drives the shift in the equilibrium towards the more polar, more ionized form of ketoprofen, and that's what's responsible for this drop in retention factor. So this pressure-driven change in retention, and potentially if we have more than one analyte present, a pressure-driven change in selectivity is quite well documented now. It's been observed by a number of groups and can become quite important when considering translating methods to high-efficiency UHPLC format columns. And so it's definitely something to watch out for. So that really concludes our discussion on small molecule analysis. So what I want to do now is move on to looking at the analysis of large molecules. We have a large molecule on the screen there. This is a monoclonal antibody, has a molecular weight of around 150 kilodaltons. which of course is substantially larger than the size of a small molecule, which should typically be around the range of, I'd say, 150 up to perhaps 1,000 daltons. So because of their size, they behave very differently when we chromatograph them, and that gives us some different considerations when we're developing method. And broadly speaking, we're again looking at reverse phase, so a similar set of parameters should be considered when developing methods on large molecules. So again, we need to consider the pressure. Column dimensions, particle sizes are also important, and pore size, as we mentioned, is really critical. You need essentially a much larger pore size, around 300 to 500 angstroms, for our protein to actually be able to interact with the stationary phase. And we'll look at that in a little bit more detail in a minute. Column chemistry is also important. Solvent type, temperature, pH can be very important. We're going to look at some examples of how we can consider those factors in a short while. So reverse phase analysis of large molecules can be somewhat difficult for small molecules, as we primarily have a continual movement of the analyte in and out of the stationary phase as it migrates down the column. And so we can get some nice isocratic separations. Now, protein is very different. We can't generally use isocratic separations, and you can see that on the right-hand side as we change the percentage of organic in the mobile phase on an isocratic mode. We get very different separations, and we can end up with some quite long retention times, and that's essentially related to the fact that proteins and their degradants can have quite large spans of retention factor. However, so that means that typically we use gradient separations for large molecules for proteins. But this can be problematic in itself. We've got potential for denaturing of the protein, which can cause irreversible absorption onto the column. In general, there's a somewhat of a lack of understanding of the exact mechanism that operates with large molecules. Essentially, what we believe is it's more of a, rather than the constant partitioning type of interaction that we see with small molecules, we have much more of an absorption type interaction with the stationary phase. Essentially, the protein is a very complex molecule. You have a lot of different surface functional groups, and within that you'll have a hydrophobic region, which we refer to as a hydrophobic foot, and essentially that interacts with our stationary phase, and our protein will stick to the stationary phase via hydrophobic interactions. And as we increase the organic concentration in our gradient, we'll reach a point where that interaction is broken and the protein is eluted. So it's very much a digital on-off type interaction with proteins. In general, we find that longer chain lengths, longer ligands on our stationary phase, so CH stationary phase, C18 stationary phase, can sometimes give lower recovery than shorter C4 stationary phases. And this can lead to potentially some issues with carryover. So some general approaches to a large molecule analysis. Generally, the organic solvent, we're much more limited than we are with small molecule analysis. Acetonitrile is our preferred option. With methanol, we tend to get much broader peaks, whereas acetonitrile absolutely gives sharper peaks. So unlike small molecule analysis, it is a bit more difficult to fine-tune the selectivity for your mobile phase. There are one or two little tricks, such as the addition of isopropanol, which I'll run through in a moment. Column length tends to not be quite so important for protein analysis as it is with smaller molecules. For peptides, it can be important, but not so much for larger proteins. This is very much related to that idea of a hydrophobic foot, that absorption mechanism that we mentioned a moment ago. And temperature is important with large molecule analysis. These large molecules, they diffuse very slowly, so consequently we have to use elevated temperatures, at least, generally speaking, at least 60 degrees to help improve chromatographic efficiency. But proteins can start to denature at these temperatures, so the protein you're actually analyzing in your column is not necessarily the same structure as you inject on it. but then we consider that we're eluting an organic solvent, which also causes denaturing, so that's not necessarily such an issue. So some considerations with large molecule analysis. We mentioned that biomolecules can stick to stationary phases and column fritz. This can result in decreased recovery. It can also change the selectivity of our column. So essentially you have your nice column and you're coating it with a very expensive protein, and that's going to affect the selectivity of subsequent injections, and potentially, as you start to block interstitial spaces, can increase column back pressure. So occasional cleaning is prudent if you have strong ionic interactions. A solution such as 6-molar guanidine hydrochloride can be useful, or if you've got a very strong hydrophobic protein, washing with a high, or carrying out a gradient running to high percent or acetonitrile can be useful as well. Column back flashing can be useful, but I would urge caution with that approach. Always refer back to the column manufacturers. Sometimes back flashing is incompatible with columns and can destabilize the column bed. So we mentioned pore size is very critical. If we were to utilize the same the same 100 pore size, 100 angstrom pore size as we do typically with small molecules, we end up with a situation with A where our analyte, in this case a monoclonal antibody, cannot actually physically fit inside the pore. So for that reason we use a wider pore stationary phase. Within the Avantor ACE range, we've now launched a new range of biocolumns specifically for the analysis of biomolecules such as this, and we have 300 and 500 angstrom phases available in that range. And you end up with a situation shown in B where now your analyte can properly enter the pores, it can properly interact with the stationary phase, and you get good retention and peak shape for the analyte. So we also mentioned column temperature is very important for the analysis of biomolecules. Here you see this very clearly. As we increase the column temperature from 20 up to 80 degrees, we get a much higher peak capacity, so much higher efficiency from the column, and that's demonstrated very clearly on the right-hand side where we have one of our solid core biophases, a 300 angstrom C4 in this case, and we've got beta-galactoglobulin analyzed at 22 and 80 degrees. We see at a higher temperature we obviously get much sharper peaks, we get much higher efficiency separations and better resolution. Temperature can also affect selectivity, so if we look at this example very quickly here, we've got at the top at 40 degrees, we have peaks 3 and 2, essentially co-eluting. As we gradually increase the temperature to 80 degrees, we get quite different selectivity for those two peaks. So again, if you're struggling to separate peaks with larger molecules, taking a quick look at temperature can be beneficial. I also mentioned earlier about the mobile phase. We can potentially introduce a little bit of IPA into our B line, which can help alter the selectivity of the separation. So again, we've got peaks 2 and 4 eluting here. When we substitute a little bit of IPA into our B line, we can alter the selectivity. If we introduce a little more, we may get an even better separation there. That doesn't always work, but it's a useful tip to try if you're really struggling. So, flow rate can also affect the selectivity we obtained. I won't talk about too much because I think we're starting to run a bit short on time, so I'll just skip through this very briefly. But in relation to this talk on solid core particles, what we want to know is, do solid core particles provide improved peak capacity over fully porous materials? And the answer to that is absolutely yes. So we can see here at the top we have a 2.5 micron 500 angstrom column from our ultra-core bio range. Below that we have a 3.5 micron 300 angstrom column. And at the bottom there we have a fully porous UHPLC particle designed for biomolecule analysis. Again, that 300 angstrom pore size and C4 stationary phase. So if we look at the graph on the right, you can clearly see that those two solid core columns absolutely give higher peak capacity, high average peak capacity than that fully porous 1.7 micron particle. And the reason for this is it comes nicely background to the history of the particles. So it's actually the improvement in the C term that gives us this performance benefit. It wasn't impactful for small molecules, but for large molecules it absolutely is. It drives this improvement in efficiency. Essentially, the proteins, as we said, diffuse very slowly, so if we reduce the path length that our mass transfer can occur over effectively by introducing a Solicol, we get higher efficiency, which is exactly what we see here. So very briefly, we just got a couple of examples of the type of high efficiency separations we can generate on these columns. Here we have the UltraCore Bio C4 500 angstrom phase, a separation of a variety of different proteins and peptides, and you can see that we again generate those very efficient peaks to get very good separation. If we now take peak 5 and look at that on a much shallower gradient, you can see we again get that very high efficiency, which can help us to start to tease out different variants or different impurities within that sample. So to finish off, I just wanted to briefly show how we can utilize Solicor technology to look at a very topical class of compounds, the monoclonal antibodies. We've got a schematic of the structure here. These, again, molecular weight around 150 kilodaltons. They're very complex molecules. You can see there's quite a lot going on here. We have different chains, we have different regions of the molecule, and in the biopharmaceutical industry, we have to use a variety of techniques to look at different portions of this molecule to accurately characterize it. So we begin by looking at the molecule intact. Here we have a NIST reference monoclonal antibody on this time 500 angstrom C4 phase. We use that 500 angstrom phase because we're looking at a very large molecule now. And you can see again we can generate nice high efficiency separations. We're using a high temperature, 80 degrees, as we discussed earlier. And again, you can quite clearly see some variants pulled out and a nice level of baseline detail on that separation. We can then use a bottom-up approach where we essentially digest the monoclonal antibody at very specific sites to yield a characteristic peptide fingerprint for that molecule. This slide just details it's not a question of just treating our sample with trypsin. There's quite a number of steps to that. I'm not going to go through them now, but there's a sequence of steps that we have to go through to actually digest the protein. So here we have a tryptid digest of a smaller protein, lysozyme in this case, and we're performing the separation this time on a 300 angstrom phase. And you can see here what we've actually done is run this on 3 different stationary phases, stationary phase chemistries that we have available on the UltraCore range, UltraCore Bio range. So we have a C18 phase. The C4 phase gives us a little less retention than the C18 phase, can be good for larger proteins. And we also have the phenol 2 phase, which offers some alternative selectivity. So if you're, for example, working with mass spec detection and you're looking at some very specific characteristic peptides within this complex mix that you're particularly interested in, then different column selectivity can absolutely help you sort of zone in on difference or try to tease out peaks that you're struggling with. Here we have, moving on, a tryptid digest of a monoclonal antibody. You can see there's a lot more complexity to that. And for a complex separation like this, we need to use a much longer gradient time to really gain resolution. Again, we've got those different column selectivities, which are well worth assessing in method development. So then finally, we can look at some very specific fragments of the molecule. We can reduce the molecule with DDT, for example. This can yield the light chain and the heavy chain. We can also digest with another enzyme, papain in this case, which releases the antibody binding region, the crystallizing fragment of the molecule. And then we can also do IDES digestion, another enzyme here from Streptococcus pyogenes. And then after that, we can further reduce the molecules in DDT to yield some additional fragments. And this final chromatogram just sort of shows overlays of those particular analyses. We have the Intract trastuzumab in this case, and then we've digested that and enzymatically treated to yield these different fragments. And again, once again, the solid core particles are ideal for carrying out this sort of analysis. So that concludes the body of my talk for the webinar today. So just to recap, we've looked a little bit about the history of these particles. We've then taken a look at the modeling the kinetic performance of them. We've seen that they can help us generate very highly efficient separations, and also can generate separations quicker and with a lot less effort. And that's particularly, well, it's very valuable for separating small molecules. And then we've also looked a little bit about how we can utilize this technology for the separation of large molecules. And so all that remains now is me to really say thank you for your attention today. I hope this talk's been useful, and I'll pass back to Ali now for questions. Thank you very much.
Well, thanks very much, Matt. That was a great presentation. You managed to fit a lot of useful information in a short space of time, but that was great. Before we begin the question and answer session, I would like to ask our audience to participate in 2 brief polling questions. Please click directly on the screen to enter your answers, and if you could answer them, that would be a great help. And the first question is, would you be interested in learning more about Avantor ACE ultra-core columns? And that's just a yes or no. I'll just repeat that. Would you be interested in learning more about Avantor ACE ultra-core columns? And that's just a straightforward yes or no. So thanks very much for participating in the first poll. And I'd now like to ask our audience to participate in our second polling question. So please, again, click directly on your screen to enter your answer. And here's the next question. Do you feel like you learned something about solid core separations or method development today? And that's just a yes or a no. And I'll just repeat that. Do you feel like you learned something new about solid core separations or method development today? And thanks very much for participating in our second poll. And as a reminder, if you have a question, you can submit questions by typing them in your Q&A box, which can be found on the right-hand side of your presentation window. And the first question is the loadability of solid core columns the same as fully porous? That is, can I use the same injection volume and maintain the same peak shape, especially for more hydrophilic early eluting compounds, Matt?
So yeah, that's a good question. So there are several aspects to this. So we mentioned earlier that by replacing a large chunk of our particle with that solid core, we reduce obviously reduce the porosity, but the column volume there. So consequently, the surface area of the particle drops considerably. But as I mentioned, with the current design of solid core particles, they're still roughly about 70% porous. So whilst many years ago people considered that solid core particles had much poorer loadability than fully porous particles, that same situation doesn't really exist today. What I would say is if you're moving a method to from fully porous particles to solid core particles, what you've got to do is take into account that you're essentially reducing your column internal volume, because a large proportion, a significant proportion of the column internal volume is now taken up by that solid core. So what you can do is, instead of injecting the same amount, what we typically do is we scale the injection volume to the column volume, and there are lots of fundamental equations that describe how we do this. What I would suggest is, if you look at the MacMod website, you'll be able to download a translation tool that we've developed, the ACE translation tool, and that can be used to perform those sort of calculations. That's probably worth a look for that, I think.
Well, thanks very much, Matt. Will Avantor be offering ultra-core SCX or SAX columns in the near future?
Again, that's a good question. I think that as far as I'm aware, there aren't too many ion exchange phases available on solid core particles. I think they, if I remember rightly, they tend to be polymeric-based particles. I think probably the answer is I don't think there are any plans at this stage, but I don't see as I think as the technology becomes solid core particle technology becomes more ubiquitous, that will eventually happen, I'm sure. But sorry, I can't really give a particularly definite answer on that one, I'm afraid.
Okay, thanks very much, Matt. And the next question is: do you have any column regarding charged molecule separations?
So charge, I'm assuming that they're talking about sort of charge variants for monoclonal antibodies. Certainly, we don't have any columns available in the ACE range as of yet for that type of analysis quite yet. We do have some stationary phases available within the Hycron brand and potentially from other manufacturers as well. But as I say, not in the ACE ultra-core range at this current time.
Well, thanks a lot. And there's another question here for you, Matt. What selectivities are available in fused core, and what would you recommend for method development?
So we've got quite a range of selectivities available. So for small molecules, we have a C18 phase, a biphenyl phase, the C18 amide phase, and also the phenyl hexyl. Those are all available on a 3.5 micron particle size. Additionally, we also have a super C18 and a super phenyl hexyl. These have a unique surface encapsulation, which basically means that we can utilize those at high and low pH. So essentially, there are 6 potential options for small molecules. In terms of which ones I would recommend, it's always worth having a C18 phase in there, but also 3 or 4 different selectivities tend to be good, and what we'd suggest is that for method development you look at initially screening your sample on a variety of different stationary phases to identify which one's most applicable for your separation. On the large molecule side of things, as I mentioned, we've got this new ultra-core bio range. We have 300 and 500 angstrom particles, and each of those are available with either a C4, a C18, or a phenyl 2. That's a sort of diphenyl ligand, which again can give us some different selectivity. So again, with method development, it's a good idea to assess multiple selectivities for large molecules as well. It can really help you out.
Well, thanks a lot, Matt, and thanks for taking those questions, and thanks a lot. That was a great presentation. Unfortunately, we're out of time. I want to thank the audience for attending and for participating in today's event. I would also like to thank our sponsor, MacMod, for making today's webcast possible. You will receive an email alerting you when this webcast will be available for replay. We do invite you to send this announcement to any of your colleagues who may have missed today's live event. Thanks very much for attending, and we look forward to seeing you here again. All the best. Bye.